inverse relations. Just like the mathematical operations have inverse. Multiplication has division, addition has subtraction. Functions have inverses as well, and relations have inverses. So inverse relation, basically you swap the x and the y's around. So if y equals function x is a relation, its inverse relation would be x equals f of y. Now you might rearrange that there to make y the subject so it becomes more obvious. But that's basically how you find the inverse. You swap the x and the y around. Because what inverses do is cancel each other out. So you may or may not realise you've been doing it. For instance, do you remember solving exponential equations where we said, log both sides? Remember that idea to solve it, log both sides? And that's because the logarithm function is the inverse of the exponential function. So when you log both sides, you cancel the exponential out. And that's why it worked. If you had y equals, and it was a square, to undo the square, you would square root again, because they're inverse operations. So all these relations have an inverse. So y equals x cubed plus x, its inverse would be x equals y cubed plus y. Now that's a bit tricky to make y the subject of, so we probably just leave it like that. That therefore means the domain and the range swap around. So the domain of the original relation becomes the range of its inverse relation. And vice versa. So the range of the original relation becomes the domain of the inverse. If you were to draw both of them on a graph, they would be reflections of each other in the line y equals x. So y equals x squared, our parabola, its domain's all real x, and its range is y is greater than or equal to 0. Its inverse would be x equals y squared, and the domain of that is x is greater than or equal to 0, and the range is all y, all real y. So they swap around. And if you were to draw both of those, and hopefully if you use a little bit of imagination, you see they reflect in y equals x. But it also means if you wanted to find those points of intersection, one's obvious, of course, but you could just make y equals x and solve that equation. Inverse functions are far more important. Not a lot of functions have inverse functions, because here's the rule. If the inverse relation of a function, so you're starting off with a function, but of course a function is a type of relation, you find its inverse relation, swap the x and y's around, but if that answer, that result, turns out also to be a function, so it satisfies all rules for a function, then we call it an inverse function. Wow. All right? How can we test to see if something has an inverse function? Well, if all we're doing is swapping the x and the y's around, remember we said there was a really easy visual way of seeing if something was a function. Good. Straight line test. Vertical. Well, if I'm swapping the x and the y's around, to look at the original function, all I've got to do is a horizontal line test. If it satisfies a horizontal line test, then it will have an inverse function rather than just an inverse relation. Well, what I'm saying is, if I look at the parabola right there, y equals x squared, now I want to know, does that have an inverse function or just an inverse relation?
So you did the horizontal test.
So you look at it, give it a horizontal line test. Does it pass or fail?
It fails.
So it would not have an inverse function.
But it, have an inverse.
But it will have an inverse relation. And that's when you swap the x and the y's around. So we use a horizontal line test. Of course, this was a similar idea, if you remember, for when we tested for functions. We could use algebra. When x equals function y, so you've swapped the x and the y's around, if you rewrite it and make y the subject and it is unique, then we know that is a function, so it'll be an inverse function. So all right, there's our parabola, y equals x squared. Now, fails the horizontal line test, no good. So we know it only has an inverse relation, not an inverse function. If I did it via algebra, well, swap the x and the y's around, x equals y squared. There's my inverse relation. If I try and make y the subject, I get plus or minus. Two possibilities. Not unique. So no, it does not have an inverse function. Whereas, say, the cubic satisfies a horizontal line test. So yes, it will have an inverse function. If I swap the x and the y's around, there it is, x equals y cubed. If I make y the subject of that, I get y equals the cube root of x. But not plus or minus, it's just y equals the cube root of x. So it is unique. There is only one possible answer there. So yes. Okay. Here's the really cool thing. You're going to love doing some of these. Trust me, you will enjoy it. Anyway, if the inverse relation is a function, in other words, it has an inverse function, then what we should see is this. The inverse of the function will equal x. It should cancel each other out. So if you substitute the actual function into the inverse function, you should get the answer x. It'll all cancel. And the other way around should work as well. If you substitute the inverse function into the function, you should just get x as the answer. Here's the function we're going to play around with. X minus 2 and x plus 2. What is it? Correct. Hyperbola. Why do I know that? Well, there's a pronumeral in the bottom, pronumeral on top. That's probably going to be hyperbolic. I could also do a polynomial division on that, and it ends up being 1, what do we get? Minus 4 on x plus 2, something like that. But anyway, let's find its inverse. So I'll swap the y's and the x around, but I want to make y the subject. A little bit of algebra, we get there. There's the inverse relation. At this stage, it's the relation. I'll pretend I don't know what this looks like. So, is this an inverse function? Well, if I substitute in the function into the inverse. So everywhere I see x, I'm replacing it with x minus 2 on x plus 2. Now, if I can simplify that down and get the answer x, then I know it works. So let's just keep going here. A bit of algebra playing around. We get the denominators the same, but we do end up with x. But the reverse should be true as well. So this time, I'm substituting the inverse into the original function. So everywhere I see x, replace it with 2x plus 2 on 1 minus x. Again, a bit of playing around with the algebra to do. But yes, it does turn out to be x. Everything cancels. Draw it. Now, if I had to draw it, remember we knew it was the reflection? So I'd probably draw myself in y equals x, and now I'll just transfer key points across. Now, any point of intersection there will stay on the line, because if you're reflecting the light, it'll stay there. Oh, there we go. Oh, gee, that's a nice drawing. But some of the key points I would pick would be like the turning points, because then when I reflect through, I know I'm going to get a turning point. And so, and I'd probably just get my ruler if I want other points and slide it along y equals x, but you've got to be at 90 degrees, and then just pick a point, reflect it across. Pick a point, reflect it across. But when you turn your head 45 degrees, you go, oh yeah, how cool is that?